Hey guys, welcome back. Today we are going to dive more into equations for a batch and a continuous state tank reactor. But just a quick recap, we derived a general mole balance for a batch reactor and we got to this equation here when everything is perfectly mixed. Of course, we also did for a constant volume and at constant pressure. And we also derived a general mole balance for a continuous state tank reactor. Before we dive deeper into examples and practical, I want us to also look more into more equations that you should familiarize yourself when we talk about continuous state tank reactor and a batch reactor. Of course, there are more reactors, but we are mainly focusing on those two. Recap, we also looked at non-elementary and elementary. We said for a non-elementary, the stoichiometry of the reaction order of each species is not identical, versus when it's elementary, it's identical to the stoichiometry coefficient for the species of the reaction. You can see for non-elementary, the orders are unknown, hence represented in form of beta and alpha. For elementary, we can take the stoichiometry coefficients in front of our equations and simply substitute them as our orders. So the forward, reverse, and overall. Let us also define conversion. Conversion can be defined as the number of moles of A that have reacted per mole of A fed to the system. It's basically moles reacted divided by moles fed to the system. For a batch reactor, we are working with number of moles, hence N. So Na0 simply means the initial fed to the system, and Na simply means that which should be left at the end of the system. For a continuous state tank reactor, we are working with molar flow rate. So our mole is divided by time, so it's mole per time. We have molar flow rate that enters the system and molar flow rate that exits the system. Okay, now let's design equations for an ideal reactor for a batch system and also derive the time necessary to achieve the conversion X. Looking at this equation here and assuming that it's irreversible, we can derive the following equations. So the moles consumed or reacted in the system can be represented in this format here and furthermore derived in this expression here. Previously, we derived a batch system mole balance. We can further express it into this expression here by just simply taking this expression here and simplifying it here. Simplifying further, you will get here. You can rearrange the equation, making dt subject of the formula, or the other way around. We can integrate this expression over here, as shown below here, which therefore results in a batch reactor, the time necessary to achieve the conversion X. For a continuous state tank reactor or continuous flow, we can also explore different equations. In this case, instead of using N, we are using molar flow rates. In this expression, we'll use F. And FA simply is the molar flow rate of A leaving the system, and FAO is the molar flow rate of A fed into the system. If you know the ideal gas law, it is pressure volume equated to number of moles with the gas constant and temperature. The number of moles can be equated if you make the subject of a formula, and we know that number of moles over volume is basically concentration. Hence, we can simplify it further. In summary, we can represent our rate using this expression or our volume using this expression.